Okay, so the real subject, of course, is knots and lengths and how they relate to braids. I think Mina asked me to talk about lengths and life, so there'll be a little bit of life in the form of physics at the very end, but anyway, be as it may. So, like with my talk on braids, I want to talk mainly through pictures and then formalize some of it as mathematics. And the thing that I want to begin with is, let's see if I can get this to work. Let's see here, is it?
I think you got it backwards again.
Oh, well, that would do it. There we go, thank you. So this is the trefoil knot, which is we will presently see as whatever a knot is. It's something you take string and you wrap it around, cross it over and under, and then tie the two ends together. That's a knot, and as with many of the things we've looked at, the question is, when are two of these things equal? And is there a trivial such thing? And when are things equal to the trivial thing or not? I think Alex already mentioned it, the unknot. So anyway, this is the trefoil knot. It has overcrossings and undercrossings. So right here, if we begin at this little black dot, we have an overcrossing, and then we have an undercrossing, and then an overcrossing, and then we repeat, but we're not going to worry about the repeats. So it can be described as we've got an over, an under, and an overcrossing. And there are various ways that you might try to start thinking about knots, and one obvious thing that you could write down is the crossing number. And the question is that really a good way to think about knots or not? So I have to worry about my machine going to sleep on me here. So of course, we can't really proceed until we think about the simplest possible case, which is the one at the top. Just a nice circle oriented either counterclockwise or clockwise. And well, here we can see the first beginnings of the equality question. So if we take this piece of string and we just grab a little piece of it and twist it, we get something that we want to regard as equal to it. Okay? So this is already mentioned in the previous talk. This is one of the Reitermeister moves. Sergei mentioned this. Another thing we can do, I think he called these, let's see, there were twists and there were, pokes, that's the way you call them. So you can grab a loop and you can drag it underneath or over another loop. And again, that's something that you can undo without cutting the string. So this knot and this knot and this knot, and I think this knot are all equal to each other, okay? So the big question is this so-called trefoil knot, is it equal to the circle or not? It doesn't look like it, but maybe some extremely clever person can find some weird way of unknotting it without cutting it. And so, well, in order to answer this question, we've got to develop a little bit of mathematical formalism. And so to begin with, I want to codify these so-called Reitermeister moves. So we have the twist, we have the loop, which I think I like Sergei's terminology of the poke a little bit better. And then you have the, I can't remember what he called it, but anyway, we can take one strand and we can move it over or under the other, over a crossing. Okay, so the point of these is that if you have, see, a knot really exists in 3-space. And of course, we can only draw pictures in 2-space. And so the way you draw a picture in 2-space is you imagine shining a light on the knot onto a piece of paper, but you do record the information of whether it crosses over or under, okay? And there's something that, we mathematicians always have our special lingo for things. Not all knot projections are equal to one another. If you shine the light from kind of a random direction, then the knot will be in what's called general position, which means that when things cross, they only cross 2 at a time. You don't have triple crossings. And you see, if you did have a triple crossing, you could move the light just a little bit, and then you wouldn't have a triple crossing. It would separate those things. You just try the experiment with yourself. Take some soda straws or something and move them around. You'll see what's going on. Question? Or is it a bless you? So the point is that these so-called Reitermeister moves completely describe what happens when you have two knots in three space and if you move one to another by an isotopy, that is, you smurf it around in three space, and then you consider their projections. You smurf one projection to the other by Reidemeister moves. Okay? So the thing we're going to look for are what are called invariants. An invariant is something that if you calculate it using one projection and you calculate it in another projection, you get the same answer. Or if you calculate it using one, you take your knot and you isotop it and you calculate projections and you calculate your invariants, and then if they're isotopic, you should get the same answer. The upshot of that is, if you have some beautiful invariant, which we haven't even described yet, but we will, you calculate for the trefoil knot, you get a certain answer. You calculate for the unknot, you get a different answer. If those two things are different, you know for sure that the trefoil knot cannot be smurfed around to give the unknot. Okay? So I'll sort of repeat that argument when we actually do the invariants. So I'm going to talk about a very simple invariant. Sergei, I can't remember who mentioned this, but they're much more powerful invariants. You can look at the the fundamental group of the knot complement. That's a much more powerful invariant than what I will describe. The advantage of what I will describe is that it's quite elementary. And it's actually an instance of an example of the representation theory of knot groups, but I won't really look at it from that point of view. So, excuse me. So, a knot is tricolorable if you can color the different strands of a knot according to the following two rules. The first rule is at least two colors, and the second rule is that whenever you have a crossing, they are either all the same color or they are all different. Okay? So let's take a look at, let's see if I've got the right direction here. So if we look at the trefoil knot, that verifies this condition because here we have a red strand. We have three strands. Here's a crossing, and at that crossing we have three different colors. At this crossing we also have three different colors, and likewise here. So it is tricolorable. Now there's obviously no way to tricolor the unknot because there's only one continuous strand, and once you decide a color, that's it. Okay? So now the question is this really an invariant? If it's not an invariant, then this little game of coloring, it's beautiful, but it buys you nothing. So the whole story, I claim, is contained in these pictures here. And what I'm going to show you is that if something is tricolorable and you make a Reidemeister move, then it's also tricolorable after the Reidemeister move. So we'll take the trefoil knot as an example, but the reasoning here is really quite general. So if we do a twist, well, here we've got something that's tricolorable. Twisting it, obviously, it's completely irrelevant. Okay? Here we're going to do a poke. Let's see, here we go. So we take the trefoil knot and we take the blue loop and we poke it upwards. Okay? Now once we do that, as it stands, this is not tricolorable. But that's not what tricolorable says. It doesn't say that, your given thing when you move it around remains the tricoloration. The question is there a tricoloration of this poked knot? And of course there is, because all you do is you change the color of the little strand on the top, the little loop up there. So that works. And the same with the more interesting Reidemeister move of type 3. So here we have a copy of our trefoil knot, and I'm going to take this green loop and I'm going to pick it up and move it above this crossing right here. So this dotted green line now. And then I'll erase the solid green line, so I have this picture. And then I look at the crossing, so I have a crossing here and a crossing there, and as it stands, it's not tricolored. But I can just change the color of this strand here from blue to red, and then I'm in good shape. Okay? Alex, yes?
Can I make a little remark?
Sure.
You alluded that this is equivalent to representation theory kind of argument, right?
Uh-huh.
Meaning that you have a surjective homomorphism to S3.
Yeah.
So in the previous talk, I mentioned that part of the component of the trefoil
Mhm.
is B3.
Right.
And there is a subjective homomorphism B10 to S.
Ah, yeah, very good point.
So that does,
Yeah, yeah, very good point. Yeah, so that's really the real theoretical basis of this. Yeah.
so this was done by Fox, right?
Right, right. So the conclusion of this is that, sure enough, what seems to be obvious to our eyes is actually mathematically correct. The trefoil knot is distinct from the unknot. There's no way of moving it around to get to the unknot. And so, people have studied these things for a long time, and one of the things they've done is, they asked this question, they've made tables, sort of periodic tables of knots, so to speak. So there's the beginning of a table. All of those are inequivalent knots. I don't really remember what the notation is, but as with many things, Wikipedia is a great source for this. So the next thing I want to talk about are lengths. So here we have a picture of two linked circles, and the idea there is that, well, let's see, this picture and this picture are different. They both have a pair of circles, but the circles on the left cannot be pulled apart without breaking one of them, whereas the circles on the right can, because the B circle is, I think of it as being underneath the A circle, so we just slide it away, okay? So those are distinct lengths, and all of the things that we talked about for knots we can ask the same type of questions for lengths. Well, there's some very interesting lengths, like they're the Borromean rings, and they're sort of unusual in that A and B are unlinked. I mean, let's think about A, and let's think about B here. If you stare at it, you see that B actually is completely above A. So you can move A and B apart. You can move any pair of them apart, but you can't move them all. The whole thing is linked, okay? The question is, what is the relation of all of this to braids? And we saw a little bit of this earlier, so I'm giving the sort of the light version of it now. So here's, this is actually our sigma 1 braid, one of the generators of the braid group. And the basic idea is that you get a link or a knot by closing up the braids. And, at the moment, I'm not going to be very ideological about how we close up the braids. I mean, any way that works that I can draw and that looks nice, I consider to be fair game. So in this case, I joined the strands, that strand to that strand. I joined, I took this strand and joined it there, and this strand, and I pulled it around under. Now, if you think about that one, this is not a very interesting knot, because we can basically do Reidemeister moves on it. We can, let's see, what did I do here? We first of all, we flipped. I'm having trouble seeing my own picture now. Actually, it looks to me like we untwisted the blue strand there, and then we untwisted this, and we get this rather unappealing looking picture. It looks like something from a dental exam or something. But anyway, all of these, we move from one knot to the next by Reidemeister moves. So they all represent knots that up in 3 space are isotopic to each other. And so K, K prime, and K double prime are all equal as isotopic classes of knots, and therefore equal to the unknot. So I wrote oops because I set out to make some interesting knot or link by tying the ends of braids together, but I didn't get anything very interesting in this case. By the way, I think we may be able to stop early, which would be nice because we're all tired. So let me give a couple of other examples. So again, I took a 3-strand braid, but I decided to, sorry. So I'm linking them this way this time. I'll go over the top and similarly on the bottom. And one way to analyze this is by looking at the crossings. And stare at that for just a second and tell me whether this is an interesting knot or not? Yeah, you're shaking your head no. Yeah, so how do you see that knot as a silly knot? Yeah, you can take that, so you see that diagonal line there, if you grab that and just move it over to the side, then the whole thing is visibly the unknot. So, okay, that was my first experiment. It was a failure. So I decided, okay, let's change the crossing right here, and that's what this is. Okay, so let's look at that on the next page. So the way I try, this is really not my subject, so I'm kind of like a student at this. I just play around with things and try to figure out what's going on. So here's the knot that we got from the braid from the previous page. And then I just sort of redrew it so it looks a little bit more curvaceous. And then I used the only thing I know at this point, which is tricoloration. And yes, it seems to be tricolorable, so it's not the unknot. And actually, people who've classified these knots tell us that a knot with 3 crossings that is non-trivial has to be the trefoil knot, either oriented one way or the other in its plane projection. So, and these are some sort of failed experiments down here. So, one conclusion that we see already is that, yes, indeed, we can take braids and we can attach the top of the braid to the bottom of the braid using some rule for, in which order we combine the strands, and we get both interesting and uninteresting knots. Okay, so I guess the other thing I wanted to talk about, and again you've seen this a bit, is that we can compose knots. This is the so-called connected sum operation, and the way we do that is we've got 2 knots, one right next to the other. We just make a little break here, a little break there, and then we join the top strand here to the bottom to the top strand, and likewise with the bottom strand, and we get a new knot. So in this case, we have trefoil plus trefoil. Question?
Does it matter, like, where do we connect them, or?
I'm sorry, say it again?
Does it matter where do we connect them, or like?
No, it doesn't matter where you connect them, but that's, of course, something that needs to be proved. That's a great question, actually. Yeah, I mean, this is something a phrase that mathematicians like to bandy about is somebody says something and somebody else says, is that well defined? Well, that's an example of this question, okay, yeah. Because there are different ways of doing it, and if it gave different answers in different times, in different cases, it would mean that this is not really an operation on knots. It's something maybe not interesting, but in fact it is interesting, yeah. So, once I did this, then I asked myself, well, do we have a non-trivial knot or not? And again, my only tool at the moment is tricolorability, and I tried it and it worked, but it doesn't necessarily work. There's actually the notion of an invisible knot, which is a knot that is non-trivial. It may be detected by the knot complement, for example, but which is not detected by any of the infinitely many coloration schemes that people have dreamed up. Okay, so we can compose knots. They have kind of an arithmetic. And the very important thing I should say is there's the notion of a prime knot. So a prime knot is one that can't be written as the connected sum of 2 or more non-trivial knots. So it turns out the trefoil knot is a prime knot. And you can sort of see that because if indeed it is the unique non-trivial knot with only 3 crossings, which is the minimum number of crossings for a non-trivial knot, then it's got to be a prime knot. Okay. Okay, well, let's see if we can, I was supposed to say something about links, so we need to continue our experiments and see if we get some interesting links or not. So I'm going to up the game a little bit and try a 4-strand braid. And again, I'll just choose a way to attach the ends of the braids in a way that I find convenient, okay? Maybe not the official way, but it is a way to join the ends. Okay, so I get a link here, and if you smurf this around a little bit, you see that it kind of looks like the very first link that we had, a non-trivial link with two circles that are like this, okay? And we can ask what kind of a link we have. And well, there's the notion of a linking number, which seems to go back at least to Gauss. And the idea is this: you have a circle here, and the link is composed. The simplest links are composed of two circles. You can dip the first circle, which you think of as a little piece of wire, into soap film, and then the other circle comes around and it goes through that soap film. It goes through once, and we count that time that it goes through once, either positively or negatively, according to the right-hand rule that you learned in your physics class. So I put my fingers around the direction of the arrow on gamma 1, and I ask, is my thumb pointing along the arrow for gamma 2 or not? Well, in the first case it's not, so that has linking number -1. And in the second case the answer is yes, so that has linking number +1. If I had I could also think of another knot where gamma 2 goes like that n times. And then on the left-hand side, that picture, because I went like this, would be linking number -n. If I did, well, oh my goodness, it's another one of my bad drawings. Let's wait for it to come back to life here. Yes, what was I thinking? The arrow on the right should be going the other way. Okay, so let's review that. On the left, I do the right-hand rule. My thumb is pointing opposite to the arrow on the red circle, so that's linking number -1. If I did this 7 times, that would be linking number -7. If I corrected my drawing on the right and had the arrow going up, then that would be linking number +1, and if I did that 17 times, that would be linking number +17. Okay, so so I won't try to argue this here, but the linking number, like tricolorability, is an isotopy invariant of lengths. And so the length that goes 17 times this way is different from the length that goes once because they have different linking numbers, assuming that theorem, of course. Now, I wanted to say one thing. First of all, you have to choose a scheme for closing up your braid into a link. So in one of the previous talks, the way it was talked about was, well, we just connect the top of strand 1 to the bottom of strand 1. That seems like maybe the simplest and most reasonable way to do it. If I do that with this little braid that we used for our example, we don't get anything very interesting. I mean, you can see this immediately. This is 2 unlinked circles. Okay. By the way, this braid is described by the braid word sigma 1 times well, let's see, that actually should be sigma 3. Seem to be making more and more mistakes as time goes on here. So this gives us unlinked circles, and I just wanted to mention that, let's see, do I want to do this? Yeah, I'll come back to that in a second. I'm not going to go through all this because basically I was just having fun drawing colorful diagrams. But you see, gosh, I still have that thing wrong there, don't I? Okay, it's corrected down here, but it's wrong up here. So suppose that you want to do this and link things in the standard way. Well, one thing you could do is you could interpose this braid tau here. And then you see 1 goes to 1, and well, anyway, this was a lot of fun. And you can ask whether this braid tau is something trivial or interesting or whatever. And you can see that by, if you look at the 2 middle strands, for example, you see that you have an overtwist and an overtwist, so it's actually 1 full twist. So tau is really an interesting braid. So I probably shouldn't even show this, but I guess one of the interesting things is that all of these geometric objects can be described by a word in the braid group. In this case, it's whatever the word for tau is times sigma 1, sigma 3 times tau. And if you really did want to know what tau is, then you draw some more pictures, and it turns out to be, well, first of all, the picture is this sort of fun thing here. It's a rather long word, and so that the red braids plus our sigma 1, sigma 3 plus the red braid again is this very, very long braid word. So I'm sure Sergey's program could decompose this in a nanosecond. Anyway, I want to finish by a teeny bit of real life, that is to say physics, and that is Gauss's formula for the linking number. So if you've taken a course in electricity and magnetism, you may very well have seen this. A typical situation in which linking occurs is in electromagnetism. If you have let's imagine that this blue wire is carrying an electrical current that is flowing in the direction of the arrow. Well, an electrical current creates a magnetic field, and that magnetic field looks like a bunch of linked circles. Now, some of the circles have extremely large radius, okay? In which case they look almost like straight lines. But those circles have a linking number, and that linking number can be computed by this integral. So this is a theorem of Gauss. And it's a double line integral. Gamma 1 and gamma 2 are parameterizations of these curves. So, it's some function, gamma 1 of t is x1 of t, y1 of t, z1 of t, some vector valued function. And you can subtract vectors and take their length and cube it. You can subtract it, you get a new vector. And then you can take the dot product with the cross product of these two vectors and you get a scalar, so you can integrate. Okay, so the end point of this talk is that not only do braids have to do with knots and links, but links have to do with physics via this beautiful formula here, and that gives you a completely different way of calculating this invariant. And in fact, by using this formulation and properties of integrals, you can show that it is indeed an invariant. So, well, it was a short talk, but I think that's what we needed at this point. Thanks.